Hi everyone, welcome back to my YouTube channel, the IB Crocodile. In previous videos, we discussed the SI fundamental physical quantities and the derived physical quantities in mechanics. Today, we are going to discuss the derived physical quantities in electric physics. I'm going to do this probably on 2 videos, so keep watching for more videos, but today let us just focus on maybe 4 or 5 physical properties in electric physics and go through some concepts as well and some formulas, important formulas for both physics SL and high-level curriculums. So let us start. Let's consider a piece of conductor, metal conductor, let's say copper. And this metal conductor here has a cross-section area, we call it A, and then there's some flow of electric charges, basically electrons. So when there is a potential difference is created between 2 points or between the end of this conductor here, so potential difference creates this flow of charges, which is basically can be measured as electric current intensity. Now, we know that electric current intensity is a fundamental quantity. So what is the first derived quantity in electric physics is going to be the quantity of charge. So the formula here is going to be I, which is electric current intensity, is equal to delta Q over delta T, where delta Q here is the change of quantity of charge and the unit here in Coulomb, basically C. And delta T is the time of change, right? Or the time of change in second, SI system. I is SI system, SI unit, which is ampere, right? So now in order to express quantity of charge, Q, again, it is not fundamental. Quantity of charge is derived quantity. It's a common mistake, common misunderstanding. Quantity of charge is a derived quantity, is not fundamental. I is fundamental. So if you'd like to express delta Q in terms of SI units, what you're going to do, you're going to cross multiply. So I can say Q or delta Q is going to be I times delta T, which means Coulomb, is equivalent ampere times second. Okay. So this is now we know how to express Coulomb in SI fundamental units. Ampere, fundamental. Second, fundamental, job done. Okay, very good. So quantity of charge is our first physical quantity today. By the way, it is a scalar quantity, it's not vector quantity, even though there are some negative charges and positive charge, but doesn't mean they have direction. Okay, so quantity of charge is a scalar quantity and it is derived physical quantity. Now, the second quantity I would like to discuss here, there is a formula in your data booklet in topic 5. Okay, let me first write the formula. It links I for also electric current intensity. So I is going to be the cross-sectional area multiplied by N. I'm going to talk about N in a second. And this will be multiplied by the Q, right? Or like the quantity of charge of one charge carrier. We call it charge carrier. And we end up basically using electrons, right? But just by definition, charge carrier, right? So and then there is V. So let me go through this formula, like, all the parameters there. So I is going to be electric current intensity in ampere, right? And A here is the cross-sectional area. And I mean, normally it's a circle, as you see here, so cross-sectional area here is a circle, pi r squared. If you know the radius or the diameter of the cross-section, you can easily calculate the area. Now, unit of area in SI system is going to be meter squared. Now, quantity of charge we just discussed is in Coulomb. Now, V here is called the drift velocity. the drift velocity, which means the velocity by which, a constant velocity by which the electrons are drifting through the lattice of the metal. Okay, so it is constant. In our program here, we are going to take the average velocity, right, and we are going to call it a drift, drift velocity. So velocity in SI system, of course, meters per second or meter second minus 1. Okay, so now let's try to find what are the units of n, and then we can talk about n as our second physical quantity today, right? So n is going to be units of n is going to be ampere, right, divided by meter squared, Coulomb, meter second minus 1, right? But then we can express ampere as Coulomb per second, right? From this formula here, I is going to be delta Q over delta T. So I is Coulomb per second, so I can replace ampere, by Coulomb per second, or Coulomb second minus 1, if you like. So we have at the denominator still, I did not touch it. So meter squared, Coulomb, and then meter, and then second minus 1. Okay, let's cancel Coulomb with Coulomb, second minus 1 with second minus 1. So we end up with 1 over meter squared, or meter negative to the power of -3. So the unit of n is meter to the power of -3, which is SI, no problem. So what is n now? N is called the charge density. N is called here what? Is called the charge density, or sometimes electron density. In some textbooks, you can see also electron density. So what does it mean? It means, okay, how many electrons per unit volume? The charge density, express or refers to how many, the number of electrons per unit volume. That's why number does not have a unit, just a number, right? But then we say per unit volume, it means over volume. It means meter -3. Okay, so this is the second derived physical quantity, electric physics, right? N, which is the charge density or electron density. Okay, very good. Now, let's have a look at a sample cell. And let's just go through the different parts of this sample cell here. So, or circuit, sample circuit. So the first part here, we have a cell. Okay, this is the negative electrode. This is the positive electrode, right? And then, okay, sometimes you may see a switch here. There is no switch there, but okay, sometimes you can see a switch. Assume the switch now is closed. That means there is a current flowing into or through the circuit. Now, here is the device here. It's called ammeter. Ammeter is a device used to measure the electric current intensity. And then they have a resistor here. This is the resistor. And then when you see this symbol with an arrow like that, so basically this is a variable resistor. That means that you can change the resistance. You have control to change the resistance and then have different readings of the current or potential difference, right? So now here, the V here means a voltmeter. The voltmeter is always connected in parallel, between the 2 points that I want to measure the potential difference across. And but voltmeter is a device used to measure the potential difference. And this is my next physical quantity I would like to talk about. Okay, so potential difference V. So V is the potential difference. Now, sometimes we call it voltage. Okay, so potential difference and voltage are synonyms. Okay, potential difference, right, or voltage. Okay, so by definition, what is potential difference? Potential difference is the work done required to move a unit of charge from one point to another across the circuit. Simple as that. Okay, definitions are very important in physics. I encourage you to pay attention to definitions. They are very important. You will have deeper understanding of physics when you just know the definitions, and then you know the formula, and then you know the units, and then you will be able to answer questions and solve problems. So when I say work done, so I'll say W, work done, over Q, unit of charge, right? So work over Q. Now, the unit of work, we know it from mechanics, okay? So unit of work is joule, and unit of charge is Coulomb, right? So that leaves us unit of potential difference is going to be Joule Coulomb minus 1, okay? Now, Joule Coulomb minus 1, we give it a name. The name here is volt, okay? So 1 volt also has a symbol V, okay? So we can say 1 volt, okay, is going to be 1 Joule Coulomb minus 1. It's very important. It could be a paper 1 question, multiple choice. What is 1 volt? 1 volt is 1 Joule Coulomb minus 1, but it's not voltage. Voltage is the physical property itself. Volt is the unit. Now, you may tell me, okay, but Joule, I would like even to break it down to even more fundamental, SI unit. Okay, no problem. So we remember we say, okay, we say work done is basically force times displacement, vector product of force times displacement, right? Now force is Newton, displacement in meter. So Joule, we can say Joule is equivalent to Newton times meter. But then force is what? Force is mass times acceleration according to Newton's second law. So we can say kilogram, Newton is kilogram, mass times acceleration, which is meter second minus 2. And then we have meter there. So I can replace Joule by 1 volt now is going to be 1 kilogram, right? Meter squared, because we have 2 meters here, 2 m's, and second minus 2, and then basically Coulomb minus 1. This is again could be a tougher question, paper 1, and instead of giving you Joule in the multiple choices, actually you may see something like that. So I never memorized this. Again, you can, in 5 seconds, you can derive it yourself if you know, or like the link between the forms. Okay, so 1 volt in SI fundamental units is basically kilogram meter squared second minus 2 Coulomb minus 1. So that is the potential difference or voltage. Next. Okay, next, sometimes you may see a unit is called Electronvolt. Okay, sometimes EV, Electronvolt. What is this? Again, let's start from the definition. So Electronvolt is the work done when a charge equal to 1 electron charge is taken across a potential difference of 1 volt. The first word of any definition in physics is the most important word. If you start right, this is very important. You will continue correct. And actually it tells us a lot about the definition. We say Electronvolt is work. It means what? It means it's a unit of work. It is not a unit of potential difference. So this is very important. So Electronvolt, it should be like the non-SI unit, of Joule, for example, because we know work, SI unit of work is what? Is Joule. But sometimes you may see, no, Electronvolt is not Joule. So now let me explain, or let me present, okay, how to convert from Electronvolt into Joule. So I'm going again to start with the definition. Definition of voltage or potential difference is going to be W work done over Q. Now, and instead of Q, I'm going just to say, okay, I'm going to say I have only 1 electron. So the charge here is the charge of only 1 electron, and we call it the fundamental charge. The fundamental charge, which is actually the smallest charge exists in matter. And in your booklet, you may find it, of course. E is equal to 1.6 times 10 to the power of negative 19 Coulomb. So this is the quantity, this is the fundamental charge, the elementary charge or fundamental charge of electron. Okay. So, and now we are looking here for work done. Okay. So I have the formula here. So work done is going to be V times E or EV, and that's it. Right? So now you can see here EV, it means electron volt, which means this is the unit. I don't have now to, now I need to express E in terms of Coulomb to be able to convert this in SI system, right? So, but again, like work done, I can just say, okay, it's just EV, electron volt, right? So if I replace E by 1.6 by its value times 10 to the power of negative 19, now you get Coulomb, but then you have volt there, right? I mean, this is the volt here, V, right? So now Coulomb times volt. Now, if I multiply Coulomb times volt, what I get? If you multiply Coulomb times volt, what you get? You get the unit of work in SI, which is joule. So in other words, okay, 1 electron volt is 1.6 times 10 to the power of negative 19 joule. And this is your conversion. Unfortunately, it's not in your booklet. You need to know it. Okay, so 1 electron volt, but it's very easy to like understand if you understand what I did. You know, so for electron volt, you just multiply by the elementary charge, right, to get joule. Sometimes in some questions, you know, you may see 1 M capital EV. What is M capital EV? It's mega electron volt. So in this case, we need to like apply two conversions. First of all, I need to take care of the mega. So mega as a prefix is 10 to the power of 6. So you can say, okay, so it's 1 time 10 to the power of 6 electron volt, but then electron volt is going to be 1.6 times 10 to the power of negative 19 joule, and so on. Okay, so electron volt, again, as a very short summary, is a unit of work done, not unit of potential difference. Very good. So very good. Now, next, capacity of a cell. So let's just a quick chemistry background. You know, so a cell, just, you know, two electrodes, right? This is like a very simple cell. We have some chemicals, and there is some chemical reactions here, and these chemical reactions produce some chemical energy. And then when the cell is placed in a circuit, so this chemical energy is being converted into electric energy. Okay, so the energy transfer in the cell is chemical energy into electric energy, and that will give us the potential difference, and that will allow the charges to flow, and then we have current. Okay, so this physical property is called the capacity. What is a capacity of a cell? So let's see the definition. Definition is the constant current that it can supply for a given discharge time, and it is measured in amp hours, AH. Amp hours is not SI, but it is very common in industry. Okay, so a capacity or a cell, right, can be rated, you know, in with certain values, amp hours, AH. Now this capacity here, it depends on two main parameters or two main factors: the size of the cell's plates. So you may have actually the same chemical composition, you know, inside the cell, but from a different cell, you may have like the cell may have like bigger plates. And the second factor, the volume of chemicals. So you have bigger plates, more volume of chemicals, even with the same chemical composition, you will end up with obviously more capacity. Okay, so when you look at this amp hours, so basically we don't like hours here, because again in physics we don't use hours. What we use in for unit for time, we use second, right? So basically, like what I would do if I see, I will go through this example together now, but I just wanted to say, okay, like 1 amp hour, I will keep ampere because ampere I like is SI, no problem. But hour, I would convert it into seconds. So obviously 1 hour is 60 minutes, right? And each minute has 60 seconds, right? So then you will end up with 60 times 60, okay, amp second. I know it doesn't sound very like industrial unit, but in terms of problems, when you start to solve question, what we are going to do right now, we need to convert everything into SI system. Anyway, so let's have a look at this question here. The secondary battery for an electric drill uses an 18-volt nickel metal hybrid battery rated at 2 Ah, 2 amp hours. So you have rate, right? This is what I talk about. The drill is used continuously for 3 hours, at which time the battery is fully discharged. Okay. So the capacity, when you look at a capacity, is basically the maximum quantity of charge in, like, you know, that can be delivered during the use of the battery, right? Because like if you look at the unit, you know, ampere second or unit of current intensity times unit of time, right? And knowing that current is delta Q over delta T, right? So if you multiply ampere by second, what you get? If you multiply ampere by second, what you get? You get Coulomb, right? So actually amp hours or amp second is another way to say it's a quantity of charge. Make sense? So let's try to solve this question together. So what I would like to do, I would actually convert everything into SI system. So I'll say, okay, so we have the capacity. Okay, so wait 1 second here. So capacity is going to be 2 amp hour. So basically 2 times 60 times 60, and that will be amp second. And then we have delta T, we have the time, right? 3 hours until fully discharged. So we have 3 hours, so 3 hours, 3 times 60 times 60. So now we've got the time in seconds. Okay. So if you have capacity, amp hour or amp second, okay, that's basically, it is the charge. So I don't need to do anything actually. So number 1 here, we already actually got it. The full amount of charge originally in the battery, it's basically the capacity, but in Coulomb, right? So we say, okay, so say the full amount of charge, the Q, is going to be 2 times 60 times 60, right? Which is 3,600 times 2, which is 7,200. So 7,200 Coulomb. This is the full amount. Now, second request, determine the average current through the drill. Now, if you know the quantity of charge, you know the time, so you get the current, you just divide, right? So the current here is going to be 7,200 Coulomb by 3 times 60 times 60. Now, obviously, I could actually, do just a smart move here, 2 times 60 times 60 up. I don't have to put the final answer. And then I can just cancel 60 and 60 together. So the current is 2/3. The current is 2/3 ampere. Okay. Now, calculate the energy transformed by the drill. Okay, number 3. So energy. Oh, let's see. We have here 18 volts. So voltage is always linked to work done or energy, right? Because work done is the energy transferred from one point to another. So we can say, okay, so let's say, okay, so if I have 18 volts or, okay, volts or voltage, sorry, voltage is work done or energy divided by the Q, right? So that means in order to get the energy, or we call it actually electric potential energy, okay? So electric potential energy, I'll just call it EPE for now, is going to be V times Q, right? So we have V 18 volts. We got the charge from part one, or number one, 7,200. So basically you multiply 18 times 7,200. So what you get here, you get 129,600 joules. Okay. I am not worried now about the significant figures. We can talk about significant figures in later videos, in later sessions. But so far, I just wanted to show you the capacity, what do you mean by capacity of a cell, and how to solve some questions you may see in your paper regarding the capacity of a cell. Okay, by this, I'm going to conclude my video today, my session today, and I will hope to see you in next videos. You may like to subscribe, you may get some notifications, you know, when I upload my next part for electric physics and other branches in the program, both physics and math as well.